while the electrons are moving through a solid, electrons are colliding with atoms and losing their energy. Because of that, every solid has a resistance. But this resistance of a solid can change by temperature. How? When you heat a solid, say that it's a copper, when you heat the solid, atoms of the solid gains energy. When they gain energy, they start vibrating with a greater amplitude. When they start vibrating with a greater amplitude, electrons start to collide with those atoms more frequently and loses energy in a greater rate as well. Yani as temperature of a solid increases, its resistance also increases, except semiconductors. The higher the temperature, the larger the amplitude of the vibration of the atoms, and more difficult for electrons to move through the solid structure. And then resistance of many solids increases with increasing temperature, except semiconductor. In semiconductor, it was opposite. Okay, if resistance increases with temperature for a solid, we can do opposite. We can decrease the temperature of a solid by decreasing temperature. Let's do opposite. If we cool a substance, if we cool a solid, if we lower the temperature, so we can decrease its resistance as well. The lower the temperature means the smaller the amplitude of the vibration of the atoms, which means easier for electrons to move through the solid. Yani resistance of the material that is cooled must decrease as temperature decreases. What if we cool this substance to absolute zero? What is absolute zero? 0 Kelvin. At absolute zero, there is no vibration of the atoms. They don't vibrate. Nothing moves. So we expect resistance to be zero as well. Yes, this happens, but not for all solids. Some solids can have zero resistance at 0 Kelvin, but some solids not. So why not? Now first we will talk why not. Then after that we will talk about why. Okay. When some types of solids, such as silver is in fact the best conductor. But when you cool down the silver to absolute zero, silver does not zero resistance. Still it has some resistance. Silver, it never superconducts, no matter how cold it gets. Amplitude of the lattice vibration decreases when you cool it down. Resistance decreases as you see. Now this is the temperature horizontal. Vertical is the resistance. As temperature decreases, resistance decreases, but until 10 Kelvin, this is okay. But after 10 Kelvin, it's a constant. It never decreases anymore. Even if you get the temperature 0 Kelvin, still there is some resistance for silver. Silver never can have a zero resistance, even if you cool it to absolute zero. But why? So there must be a reason for this. Yes, there's a reason. One of the reasons for this non-zero resistance for the silver is lattice imperfection. Lattice imperfection. What does lattice imperfection mean? It occurs when some of the atoms do not line up perfectly. For example, in this classroom, there can be a lattice imperfection if all the seats are regularly arranged. If all the seats are regularly arranged, so there can be a space for me to volve and the electron. So, but now, there is lattice imperfection. She's putting the seat on my way. So when I was moving, I'm going to collide with her. So she will make my walking difficult. Lattice imperfection is this. The regular geometric pattern of the crystal or lattice is in a solid is often flawed. a student says that I cannot see from this point and then take and see another point. So then changing the geometric pattern of the classroom, of the solid. Even if no thermal vibration, no atoms are vibrating, many materials exhibit some resistance due to imperfect geometric arrangement of their atoms, which is called lattice imperfection. Silver exhibits a residual resistance because of what? Lattice imperfection. What is lattice imperfection? Imperfect geometric arrangement of the atoms of a solid, and electrons still collide with those atoms which are not lined up regularly. Okay? This is how and why some solids still have resistance even if you cool them down to 0 Kelvin, at which no vibration. But some substance superconducts, they becomes 0 resistance. How? Now we will explain that one as well. Second type of the material is the materials such as tin. When another type of material is cooled, their resistance decreases. As you see, this is the graph how resistance and temperature changes for a tin. As resistance decreases, as temperature decreases, resistance also decreases, as you see, until a critical temperature. But at this critical temperature, something is happening directly. This substance, this solid becomes a superconductor. And its resistance becomes 0. So then we should find an answer. What is happening in here? And this tin suddenly becomes a solid with 0 resistance. So resistance decreases, yes, and a temperature above absolute 0, yani at this temperature, which is called critical temperature, it suddenly begins superconducting. Any device, any solid which becomes which gets 0 resistance below a critical temperature is called a superconductor. A solid whose resistance is 0 below a certain non-zero temperature, this substance is called a superconductor. That certain temperature is named as critical temperature. Yeah, the critical temperature for different substances can be different. For example, I don't know exactly, but how much for tin? For tin, if it is 7 Kelvin, for other material it can be 10 Kelvin. For other one it can be 20. When temperature falls below this temperature, so that substance becomes a superconductor. So at critical temperature, tin becomes suddenly superconductor. So now we will talk about what it happens, okay? Okay, first, by the time this superconductivity is discovered at the beginning of the 90s, but it takes almost half century to provide a theory about superconductivity. The first theory about superconductivity is known as BCS theory, which is developed by 3 scientists in 1957, John Bardens B, Lynn Cooper's C, and Robert Schrieffer's S. BCS. BCS theory is the theory which explains the superconductivity. Why some substance becomes a superconductor below a critical temperature. Now we will talk about this theory. According to this theory, BCS theory, electrons does not move individually through a solid. They move in pairs called Cooper pairs. But above this critical temperature, they are moving individually. But when temperature cooled down to this critical temperature, and below that temperature, 2 electrons starts to move together with two friends when they are very close. They never separate. They move in two pairs, yani two electrons together. Electrons move in pairs called Cooper pair through the lattice and the superconductor, through the lattice of the superconductor. And these two electrons travel through the lattice acting like a single particle. Yani they're together, they go together. Wherever first one goes, second one also goes down. What happens to the first one, second one also happens the same. Cooper pairs. Electrons in Cooper pairs also suffer collisions. Yes, they also collide with other atoms. But collisions do not alter the total momentum of the pair. Yani, they collide with the atoms. Yes, they do. But their total momentum does not change. Normally, if you collide with some substance, something, your momentum must change because you are losing energy, you are giving some momentum to something else. But in Cooper pair, this does not happen. But how? Why not happening this? I'll see that. As one electron passed by the lattice, because Cooper pairs are two electrons. Look at this simulation. As this Cooper pair passes through the lattice, through the atoms are approaching them. You see that? Yani, the first electron pulls the lattice towards them itself, loses some momentum, but there is one more electron at the back. This time, after first electron passes by the lattice, this time lattice pulls the electron which is behind. Yani, first momentum is given to the lattice by the first electron, but later lattice is given the same momentum to the electron which is coming at the back, second electron. Cooper pair's momentum never decreases. First given to the solid, then taken to the solid back. First electron gives the momentum to the solid, then second electron takes it back from the solid. That's why total momentum of the Cooper pair does not change as they are moving through as solids, as they are colliding with other solids. If momentum does not change, which means they don't lose energy. If they don't lose energy, resistance is zero. Yeah, the first electron attracts the lattice. First electron attracts the lattice. And lattice attracts the second electron. So first electron attracts the lattice, gives some momentum to the lattice, yani solid. Then lattice, yani solid, attracts the second electron, gives this momentum back again. That's why this Cooper pair does not lose momentum. Attractive force between these two electrons is electron-lattice electron interaction. This is a music exam question. Electron-lattice electron interaction. What does it mean? Again, as I said, first electron gives momentum to the lattice, then lattice gives this momentum back to the second electron. Electron-lattice electron interaction provides superconductivity of Cooper pairs, of that material, by keeping the total momentum of Cooper pairs constant. So Cooper pairs are weakly bound. Now we understand why it happens suddenly. Because Cooper pairs form suddenly. At some critical temperature this happens. As soon as Cooper pairs are formed, this material becomes a superconductor. As soon as Cooper pairs are destroyed, it becomes a conductor. So Cooper pairs are weakly bound. Increasing temperature destroys the bond between Cooper pairs and superconductivity bands. Okay. This is BCS story, how some substance becomes a superconductor at some critical temperature suddenly. So answer is, at that temperature, Cooper pairs are formed. As soon as Cooper pairs are formed, this material, this solid becomes a superconductor. But to make a solid superconductor, you should cool the substance. down to very low temperature. How can you do that? In the beginning, two gases are used. One of them is helium, the other one is hydrogen. Helium is very rare. You know that helium is first discovered on the sun. It's not so easy to, and also expensive. But hydrogen is explosive. And they also cause superconductivity at very low temperatures. And you should cool down the substances at very low temperatures. But some materials, new class of materials have been found later, superconducts at temperature about 77 Kelvin. Why 77 Kelvin is important? Because nitrogen boils at this temperature. As it is boiling, it's taking energy from the solid and converting solid to superconductor. From now on, nitrogen is used for producing superconductors. At this temperature, nitrogen becomes gas. At this temperature, some materials turns to superconductors. Superconductors are used in some important places. One of them is the property of the zero resistance and superconductivity would be very advantageous in low-cost electrical power transmission. Remember, we said that when we are transferring the power from Dukan to Süleymaniye, some power is lost on the way because of the resistance. If you use a superconductor, will there be energy lost? No. But superconductors, of course, expensive. We cannot do that. If you find a way to make it cheaper, so we'll use it. Okay. Second one is superconductor rings could be used as a storage device for electrical current and energy. What does it mean? You are making a superconductor ring. You are giving electric current to this ring, and the electric current starts to circulate on the ring. Because it's a superconductor, it never loses energy. If never loses energy, this electric current will circulate infinitely until you take it back. Just like a capacitor. You can store electrical energy on a superconducting ring. Second one is this. Third one, two superconductors can act an electronic switch. Electronic switch is a transistor made with superconductors. This is not explained in your book. What is it? Just name is given. I searched the internet. It is a transistor with a superconductor. Only know what superconductors are rare. This is enough. But the fourth use of the superconductor is very important. Magnetic levitation trains. Runs on superconductor magnets. What is magnetic levitation? Magnetic levitation is a phenomenon in which an object is suspended in air because it is repelled by a magnet underneath. Look at this. This is a magnet. It stays suspended over a conductor. How? Superconductor. How? You see the vapor? This vapor is the nitrogen. It's vaporizing. First they put liquid nitrogen. So liquid nitrogen vaporizes and cools this material to mechanical superconductor. Superconductor has a zero resistance. When a magnet approaching to a solid, what happens? Eddy currents, huh? Do you remember eddy currents? So they form circular eddy currents, and eddy currents are making a magnetic field. However, it's a superconductor. Eddy current never loses energy, so it will always circulate. As it is always circulating, it produces a constant magnetic field which blocks, stops these objects falling and keeps it stays suspended. This is magnetic levitation. And this is the model for high-speed trains. High-speed trains are done by this way. They are using superconducting wires in the electromagnets and then producing a very strong magnetic field and keeping these trains stay suspended in air and decreasing the friction. If friction decreases, speed of the train becomes so high. High-speed trains are using superconducting magnets, electromagnets, to make them stay suspended and then making them high-speed trains, which is called magnetic levitation, magnetic levitation. Fourth one. Fifth one is superconducting magnets are already used in high energy particle accelerators. You know, magnetic field is used for changing direction of the particles, huh? These particle accelerators have a circular shape. So you should keep particles, yani charged particles can be proton or electron, generally protons are accelerated, on this circular path. How can you keep it? How can you keep them on a circular path? By using a magnetic field, but we need a very big magnetic field. This big magnetic field can be provided only by big electric currents. Big electrons are provided by, of course, superconductors. They use superconductors in these particle accelerators. And last one is, it's the sixth one I think, MRI machines. MRI machines are also using magnetic field, but very big magnetic field, which is 30 Tesla. And such a huge magnetic field can be provided only by a very big electric current. So big electric current can be provided only by superconductors. So that's why this room is generally cold. Generally cold. Why? Because superconductors can be obtained only at low temperature. That room, that's why it's cold. This is the last one of this superconductor where we use them. And know one thing, superconductors can never be used as a heater. Why? Because they don't have resistance. If no resistance, no energy produced by a conductor. Superconductors cannot be used as a toaster. Which of the following cannot be used? In which of the following superconductors cannot be used? Toasters. Because toasters need energy. So energy appears when there is a resistance. In superconductors, resistance is zero. So by using a superconductors, you cannot produce electrical energy. No loss energy in superconductors. Okay, this is all.